Aldehydes and ketones. Carbonyls including aldehydes and ketones. Carbonyls are compounds with C double bond O. They can be aldehydes or ketones. Intermolecular forces in carbonyl. Pure carbonyls have no hydrogen bonds, but they're attracted by permanent dipole forces. Solubility in water. Smaller carbonyls are soluble in water because they form hydrogen bonds with water. Reactions of carbonyls. Carbon double bond oxygen polarized because oxygen is more electronegative than carbon. Positive carbon atom attracts a nucleophile. Carbon-carbon double bond is alkene and carbon-oxygen double bond ID stronger and doesn't do addition reaction. This is different to electrophile that attacks the carbon-carbon double bond. Oxidation reaction. Potassium dichromate is oxidizing agent that causes alcohols and aldehydes to oxidize. Primary alcohols oxidize to aldehyde, then to carboxylic acids. Secondary alcohols are oxidized to ketones. Tertiary alcohols did not oxidize. Aldehydes oxidize to carboxylic acids, but ketones can't be oxidized. Oxidation of aldehydes. Aldehyde to carboxylic acid using potassium dichromate and dilute sulfuric acid. Do this by heating under reflux. For this reaction, you'll see a color change as dichromate ions, which are orange, reduced to green chromium ions. Aldehydes can be oxidized using Fehling solution or Tollens reagent, used as tests for presence of aldehyde groups. Tests for aldehydes. Tollens reagent form silver mirror in aldehydes and not ketones. Fehling's reagent blue to red in aldehydes and not ketones. More on this in the organic analysis video. Reduction of carbonyls. Reducing agents like NABH4, sodium tetrahydridoberate, or LiAlH4, lithium tetrahydroaluminate, will reduce carbonyl to alcohols. NABH4 in aqueous ethanol at room temperature and pressure. Aldehyde reduced to primary alcohol. Ketone reduced to secondary alcohol. NABH4 has nucleophile hydride ions which are attracted to the positive carbon in carbon-oxygen double bond. Catalytic hydrogenation. Carbonyl can be reduced using catalytic hydrogenation. Use hydrogen and nickel catalyst under high pressure. Aldehyde and hydrogen forms primary alcohols. Ketones and hydrogen form secondary alcohol. Addition of hydrogen cyanide to carbonyl to form hydroxynitrile. Carbonyl to hydroxynitrile using potassium cyanide and dilute sulfuric acid at room temperature and pressure using nucleophilic addition. Potassium nitrile uses nucleophile cyanide ion. Sulfuric acid has H+ ions needed in second step of the mechanism. When naming hydroxynitriles, the cyanide becomes part of the main chain of carbons, and it's carbon 1. Use HCN for reaction, but it's a toxic gas that is difficult to have. KCN or NaCN are still toxic because of cyanide ions. Another advantage is KCN or NaCN is that there will be a higher concentration of cyanide ion as these compounds will completely ionize. HCN is weak acid and so partially ionizes. Nucleophilic addition of HCN to aldehyde and ketones when planar carbonyl group is attached equally from both sides by HCN attacking species, so racemate forms. Equal chance of both enantiomers forming and no optical activity.